Hi, this is Paul from Foresight Tech. In this video, we are going to deal with the power series, in which each term is a power function, and we will focus on determining convergence of a power series. Let's see the outline. First, I will introduce the power series and the convergence theorem for power series. Next, we will practice 3 questions together about how to use the convergence theorem. Last, I will introduce a proof for the convergence theorem. Let's see the material. Here is the definition for power series centered at 0. So let me highlight. Okay, it's centered at 0. So this time I look at the series, infinite series. This is no longer a series of number, but a series of function, right? And see, each term is a power function this time. That's why we call the power series. So this is a power function. And the coefficient here usually is Ci or Cn. We call the coefficient, infinite terms. And we look at this summation a little bit different from number series. For number series, n start from 1, right? Because a1 plus a2 like this. And this time, because our term start from a constant number, which is the power 0, therefore why we use this n start from 0. Okay, if we ignore the index, if we only write the sigma summation here, it's still the same. Okay, it's called start from 0. Let me give you a special case. Let's look at if we put Cn equals 1, what kind of series we can get? Okay, this time what do we have? We have sigma summation 1 each term times x raised to the nth power. N start from 0 to infinity. If you write open, and then the first term is 1, right? The second term is x. The third term is x squared, and then x the third power, and then plus goes on. And this is famous, right? So we learned before, this is geometric series. What is the common ratio? Okay, the common ratio R equals what? Equals x. And this time, so we can get this kind of results. And this series converges when what? The common ratio absolute value of x less than 1, right? Only. And what? Diverges when the absolute value of x or r greater than or equals 1. See? And this is the special case. Of course, we have this kind of question raised when the series converge, when the series diverge. And this kind of, we usually call it the domain of the series. Okay, and this series is important. Okay, power series is the foundation of a Taylor series, and which I will introduce later in other videos. So now we have another this, and first we send it at 0. We can extend this kind of series to power series, send it at a. If I put here, let me highlight, send it at a, which means each power function this time goes to x minus a, right, raised to the nth power. Okay, of course, you know, this is just a general case. Or you say it's a general form of a power series. And if we take a equals 0, what do we have? X minus 0 is x. So this power series goes back to centered at 0, right? This time is centered at 0. Therefore, goes back to the first special case. And now, let's go on to answer these questions. How about the domain? We need to talking about the convergence of power series, convergence theorem. Let's see the convergence theorem. Here is the convergence theorem for power series. And if we have this theorem, we can tell where is the domain for power series. Let's see. For a given power series, which is the general form, right? there are only 3 possibilities. Let me highlight. What's the 3 possibility? Okay, the first, it converges only when x equals a. Only converge at one point x equals a. At least we know when x equals a, the power series converge, right? Because we prolong x equals a inside, all the other terms disappear. Only remain the first term, which is C0, of course converge. And the second case, it converges for all the real number x, which means all the number between negative infinity and infinity, it converges. The domain is all the real number. Okay, this is the second case. If the first 2 cases are not true, and the third case should be true. What is the third? There is a positive number r such that the series converge if the difference between a and x less than r. Okay, remember how to say this? Usually we say is the neighborhood of a, the r neighborhood of a, which means when x go inside the r neighborhood of a, converge, and outside of the r neighborhood of a, the series diverge. And let me see. This r in the third case, we have a name. We call the radius of convergence. This is the most important parameter. And how to determine this r? And the 2 methods that you can use, either ratio test or road test. Okay, so we learned these 2 tests before. We're going to show you, okay, in example. And how about the third case? How about the first case? Let's see. If we use this neighborhood, okay, the concept to look back to the first case, and x equals a, what is r? Imagine, okay, no r, right? So all you say r equals 0. Why? Because only 1 point. Okay, in this case, r equals 0. How about the second case? Second case converges for all the x. R is large enough, goes to infinity. Okay, and the third case, of course, we have one case missed, which is the distance equals r, right? Can you see? I will highlight it. Okay, in the third case, further step is needed if x minus a equals r. And I will going to draw a graph, okay, to show you how to understand this theorem. Let me draw a number 9 first. Suppose the number 9 here. And we put a, which is the center, right? If I put a here, then we draw a neighborhood. If this radius is r, if this radius is r, can you see what? From the left endpoint to the right endpoint, this is what? This is the neighborhood. Let me highlight the r neighborhood. Okay, we know this is the r neighborhood. If we're going to describe, which is this way, which is the distance, I guess, to a less than r, right? Okay, so what is the left endpoint, which is a minus r? What the right endpoint, a plus r. Okay, so this is what, and just the theorem, the third case gave us, and this converge, right? So inside the neighborhood converges of the series, and another is outside of the neighborhood diverge. Remember? So what? So how to describe? In this side is diverge. On this side also diverges, right? If we describe it in this way, this time is absolute value x minus a greater than r, right? And also this diverge is x minus a absolute value greater than r. If the special, you can put this is a open interval from negative infinity to a minus r, right? To a, or you can say, let me see, minus r. So this is a open interval from a plus r to positive infinity. Can you see? This is what the theorem gave us. And then we have a special case. Look at it now. Is how about this point? How about this point? How about this point? The theorem did not give us any results, right? So this point we say is x equals a minus r, the end point. This is the right end point, x equals a plus r. The theorem did not give us any results. So for these 2 points, what do we need to do? We need to test, okay, separately, okay. And I give you another example, another definition. So we have a interval of convergence. So R is the radius of convergence, right? And this is an interval, is the domain, which is, so however, we have a different possibility. So let me show here. All the possible for what? All the possible interval, we have a name called the interval of convergence. Okay, so this we call it the interval of convergence. We have a different, because for this endpoint we have a different cases. Sometimes converge, sometimes diverge. Therefore, how many interval converges? So we have 4. Let me show here. We have 4 cases. The first, which is a minus r to a plus r, right? That's an open interval, which means both endpoints diverge. And the second case is a minus r to a plus r. This is a closed interval, which means both endpoints converges, right? This is the intervals of converge. Of course, we have another 2, which is the left closed, a minus r to a plus r. This open is also possible, right? The last case is a minus r open, a plus r close. And these 4 cases we call it the interval of convergence. And how to prove this theorem I will introduce later. But first, let's practice questions how to use this convergence theorem. Here is the first question. We have a series. Can you see this is a power series, right? It's centered at 0. N started from 1, does not matter, okay? So if n started at 0, which means the first term is 0, okay? So this is the power series. We need to find the radius of a convergence and the interval of convergence of this power series. Let me show. And this is centered at 0, right? Okay, which means a equals 0. How do you find the radius of convergence? Do you remember? Either use a ratio test or use a road test. Which one we're going to use? And we will choose a ratio test. Why? Because we have a factorial. Okay, we learned that before. If we have a factorial, the best way is to choose a ratio. So I will going to find the limit of the ratio of am plus 1 over am. I will put the am plus 1 to here, which is m plus 1 the factorial, and the x raised to the m plus 1. This is an plus 1. An is the factorial of n times x raised to n the power. How to simplify? Of course, I will say I will cancel this. What do we left? We left n plus 1. Why? If we use the definition, I will put here a little bit. M factorial of n plus 1 over factorial of n is this. Can you see? The denominator 1 times 2 times 3 goes to n, right? The top is 1 times 2 times 3 times n, and continue one more term, n plus 1. Do you remember this? That's the definition. Now we can cancel all. See, all these terms. What we left? N plus 1 left. That's why we left n plus 1. Okay, the second. We can cancel this power, right? We use the quotient law, the quotient rule of exponent. So what we left? We left x. Therefore, we simplify, we have m plus 1 times absolute value of x. Can you see this? Imagine if x does not equal 0, what the limit? Approach infinity, because what? M plus 1 goes to infinity. Absolute value x is a constant number, of course it goes to infinity. Infinity is definitely this greater than 1, right? Therefore what? Okay, remember the ratio test? Okay, the ratio test now give us this result. So, and the series diverges, right? Diverges when x does not equals 0. And how about the x equals 0? If x equals 0, can we see? X equals 0, we put here all the term is 0. Of course, it's a converge, right? Therefore, we have the result. So, the series converges only at x equals 0, right? So, converges only when x equals 0. This is the result. That's the interval convergence at one point. How about the radius? How about the r? Of course, you say this is the case, so r equals 0, right? Which is the first case in our convergence theory we just discussed. See, that's an example. So, the first case, r equals 0, exactly exists. Now let's practice one more question. Here is the second question. And we have this power series. N still start from 1. That's okay, right? And let me highlight. So we look at the series. So power series, we still have a factorial, which means what? We still use the ratio test to find the radius. Okay, let me going to find the limit of the ratio. So what? Am plus 1 over am. Okay, so this time is a little bit longer. What's m plus 1, which is I guess m plus 1, right? Over m plus 1, the factorial. Okay, this is m plus 1. And what is an, which is I guess raised to the nth power over the factorial of n. Okay, now we simplify. This is a fraction, so I can do the flip, right? So I guess m plus 1, the top, divided by the denominator, which is times the flip. Flip n factorial of n here, I guess raised to the nth power. So now, you know, we can simplify. And we just did, okay, so this and this we cancel. What we left? We m plus 1 left on the bottom. And this power, we left the x on the top. Therefore, what do we have? We have absolute value of x over m plus 1, right? Okay, take a look at it. So this is approach 0. No matter what kind of x. So for what? For all x, no matter x equals which real number, always equals 0, right? Always approach 0. And the 0 is what? 0 is less than 1, definitely. So what? So by the ratio test, see, we can find what kind of results. So we can find convergence for all the real number, right? So the series converges for all the real number x. Okay, or simply say for all x. That's by the ratio test. Then now we know what is the radius. And so the radius equals infinity, right? We simply say, which is this is the second case of the theorem we just discussed. Let's practice one more question. Here is the last question. And this time I will look at the series. Okay, so we do not have a factorial, right? Okay, so you probably will choose the road test and to find the radius of convergence. That's okay. However, you need the results. Take nth road. So the nth road of n, you know, is approaches 1. We did not develop that result before. So here, I will still choose the ratio test. Okay, and the ratio test still works. So let's going to find the ratio. Therefore, so the ratio of am plus 1 over am, which is this, is a fraction, right? So x minus 2 raised to the n plus 1's power over n plus 1. This is n plus 1. And then divided by an. An is n here, x minus 2 raised to the n's power. Okay, so this is the division. I change it to multiplication. Therefore, this is the top, right? Times the flip of the bottom. So n goes here, and the x minus 2 raised to the nth power. Now we simplify. Of course, you know, this is exponent. The exponent, what we left is 1. Okay, x minus 2 only. Therefore, we have these results. So n over n plus 1, right? The coefficient times x minus 2, the absolute value. See, what's the limit? N over n plus 1 approach 1. Therefore, no matter x equals what, and the limit always equals what? So the limit always is x minus 2, the absolute value, right? Okay, so now we based on the ratio test. Remember, so the ratio test tell us, see, if the limit, which is this absolute value less than 1, the series converge. Greater than 1, the series diverge, right? Let me write down. Okay, so let me write. So the ratio test give us these results. And the series converges, right? If the limit less than 1 diverges what? If the limit x minus 2 greater than 1. Okay, therefore this tells us, remember the graph. Okay, the neighborhood inside the 1 converge outside the 1 diverge, which means r is 1, right? Therefore we get r equals 1. And this is the radius of convergence. How do you find the interval of convergence? You remember, so what do we need to do? We need to test. Okay, now we need to test x minus 2 equals 1. Okay, so the two endpoint. So let me see. So the first endpoint, which is x equals 1, right? The second endpoint, which is x equals 3. Okay, imagine. So 2 minus 1 is 1, and the 2 plus 1 is 3. Okay, therefore, for the first, can we see? For the first, what do we need to do? We need to plug this x equals 1 into this power series. 1 minus 2 is negative 1. So negative 1 raised to the nth power this time. So what do we have for the power series? The series now is n. Is negative 1 raised to the nth power. See, this is the series of numbers. Okay, is what? Is alternating series. We learned that before. This is an alternating series. Definitely, right? And also the general term or the absolute value is 1 over n. This is goes down to 0, definitely, right? Decrease to 0. And therefore, by the alternating series test, converges this series. That does make sense? So this converges. Good. When x equals 1, the power series converge. How about the x equals 3? So we're going to see when x equals 3, if we plug into 3 minus 2 is 1. So what do we have? We have this power series. We have this series now. Is 1, because 1 raised to the any power is 1. So 1 over n. What's this series? Harmonic series. Okay, good. We get a harmonic series. Of course, diverges, right? This is a diverges. See? And therefore now we know one point endpoint converge, one endpoint diverge. So what is the interval of convergence? So now we found that the interval of convergence. See, we can convergence. So we get this. We get 1 is converge, so we put a close. 3 is diverge, so we put open. That's the result for this question. Then now we're going to prove the theorem. Here is the proof, which you can find in the textbook. It's not difficult, but a little bit long. So please be patient with me. And we do 4 steps for this proof. The first, we are going to prove that if this series converges when x equals b, you know this series is a power series are centered at 0, right? If this series converges at x equals b, then it converges when x absolute value x less than b. Okay, so this is the first. And then the second we're going to prove is the same series diverges when x equals d. And then it should be diverges b when x greater than d, or the absolute value. Okay, this is the second. And then the third, now we move to prove the theorem. The first and the second is just a foundation. And we use that, now we prove the theorem is true for x for a equals 0, which means that the power series is centered at 0. And then we're going to prove the theorem is true for a does not equal to 0, which means centered at another number, okay, does not equal to 0. Let me draw a graph to show you the basic relationship between these 4 steps. Okay, so we are going to do this. The first we prove 1 is true, right? So 1 is true. And then if we prove 1 is true, we can go to find that 2 is true. We have to use the results from part 1, okay, step 1, to prove the step 2. After we prove step 2, now we use the results from step 1 and step 2. We can prove the third step, okay, and use the results of step 3. We can prove the last step 4. Can we see? Okay, so if we prove 3 is true, prove 4 is true, therefore we prove the theorem. Now let's go into the first step. Here is the first step. If our series converges at b, it should be converges inside of b. How to prove? So we have to use the comparison, okay, test. Let me show the first. What the condition do we have? We have this. We have our series converge at b, which means b raised to the nth power. This series converge, right? Okay, we go from here. And these converge, we can get a result. And what? The limit of the general term is 0, right? So this, the general term is Cn b raised to the n. This should be equal 0. Now we start from this condition. So we're going to do comparison. But how? And this limit equals 0, which means what? This sequence will fall into any epsilon neighborhood of 0, right? If we use the precise definition. Let me show you a graph, okay, a diagram, so you know what does it mean. If we have this number 9, so approach 0, if I say 0 here, see, any epsilon, if I see this is the epsilon neighborhood, okay, the radius is epsilon, so now we have epsilon neighborhood. What our sequence is CMBN will fall into this neighborhood, right? When n large enough, or you say is when n greater than a capital N. Okay, this is the precise definition for any optional. If I pick a 1, is okay, right? So I see the neighborhood is -1 to 1 this time. Okay, which means our series is controlled by -1 and 1. Or the absolute value is controlled by 1. Okay, so I put that in language. This means given any epsilon, these are pick epsilon equals 1, we can find, right, capital N, such that when n, lowercase n greater than m, we have these results. Okay, Cn(b) raised to the nth power -0. Okay, or ignore this absolute value controlled by epsilon, which is 1. That does make sense. That's a precise definition. So now this is the major one we are going to use. Let me highlight. See, we started from here. Okay, so we're going to do comparison. How? Okay, now see we have this kind of a comparison. Our series, if I Cn x raised to the nth power, okay, so it's not easy to compare directly. We have to put the absolute value. So this time, can we see this is the big trick, the major trick we put here. How do you link it to b? So we have to do this. We have to times b raised to the nth power to the bottom, times b raised to the nth power to the top. Okay, and so it keep it the same. So here is Cn x raised to the nth power absolute value. You know it's the same, right? And if you do this, now see. And this term exactly is controlled by 1. So we have a connection. Okay. And so I wrote it into this way. So Cn b raised to the nth power times x over b raised to the nth power. Because the first term is less than 1. Therefore, this term is less than the second. The second is this. What do we do? So now we find a comparison, right? Look at it. This is the second term, the last term x over b. We have these results because we look at the absolute value of x less than b, right? So look at, so when the absolute value of x is controlled by b, and then you know we have this x over b absolute value less than what? Less than 1, right? Okay, therefore, can you see? And the right term, so here, if I put the absolute value, and this, we put the summation, this is what? This is a geometric series, okay? This is a geometric series, and R is what? Is the absolute value of x over b, okay? Of x over b, this is the common ratio, less than 1. Okay, therefore what? It converges. That's good. So now what do we get? We get our series put the absolute value is controlled by a convergent geometric series. Therefore, by the comparison, our series converge, right? Of course, I have to mention. And this comparison only works for n greater than capital N. But don't worry, okay, so finite term will not change the convergence of a series. Therefore, all the results is the same. Therefore, now, and by the comparison test. Comparison test give us these results. Okay, and this series, okay, the smaller one, which is and this is controlled by convergent, therefore this converges, right? And these converges, now we have the results. Okay, therefore our series exactly, we don't have absolute value. So our series is absolute convergent. Remember what is absolute convergent? Okay, so we know this. If absolute convergence, so converges, right? Our series. See, that's the results. So now we prove our series when x less than b, which means inside of b converges. That's the first step. Now let's go to the second step. Here is the second step. if this series diverges at D, we have to prove it diverges when x greater than D, which means outside of D, right? And this time is much easier than the first. We are going to use the results from the first step. See here, and we use proof by contradiction. Okay, very easily to get the results is true. Contradiction, which means what? And if our result is not true, and we will get a contradiction. Therefore, our result is true. Okay, so let me see. And so, how to set up our result is not true, which means the opposite. Therefore, is what? It converges at a number x greater than D, right? Which means suppose there 1x, okay, exists 1x. When x absolute value greater than D, of course, this is this we find 1x, and this series converge, right? So this is our hypothesis, but this is not true. We need to find the contradiction. How to find the contradiction? See, can you see? And we have the results 1. If we use 1, we can find a contradiction. Why? Because this time x is converges. X greater than D. You remember, their number converge, or the number inside that should be converged to, right? Therefore, the series converges at D. Okay, so that's the result from 1. Therefore, we have this Cn, we put a D raised to the nth power, should be converges to. Okay, and that's wrong. That's a contradiction. Why? Okay, because our condition says diverges at D, but now we get converges at D, therefore contradicted. Okay, does it make sense? Which means our hypothesis, this suppose, is not correct. Therefore, what? So, which means does not exist a number x greater than D converge. Therefore, all the x greater than D diverges. So, for all x greater than D, all these series should be diverge. That's the proof for this step. Now, let's go to the third step. Here is the third step. Now we can prove the theorem for the power theories centered at 0 by using the results from step 2 and step 1. Let me see, which means we can prove this series. Okay, all the 3 results. And remember, for the case 1 and the case 2, provide the example before, right? So we have to prove case 3, okay, which means this. If case 1 and the case 2 both are not true, okay, so we need to prove case 3 is true. And remember case 1, which means the radius is 0, right? Converges at 0. And case 2 is converges equals infinity, which means converges at all numbers. If our series not converge at not only converge at 0 and not converge at all numbers, so we need to prove case 3, which means what? Exists a positive number r, so that inside the R neighborhood of 0, the series converge. Outside of the R neighborhood is diverge, right? So we need to find out what is R. Let's go from here. Okay, and the first, because case 1 is not true, which means the series not converge at 0, not only. Therefore, we have 1, b not equal 0. The series what? The series let me see, is this converge, right? That's true. And also we exist another number d does not equal 0, because case 2 is not true, which means not converged at all, the real number. Therefore we have a d, and this series what? Diverge. Okay, that's the beginning. Now let's define what's the domain we need. Okay, so we define S is all the converge point, which means Cnx n's power converges. Okay, so this makes sense, right? S is what we need. We need to prove S is a kind of a neighborhood of 0. So first, let me see, this is not an m-body. That's true, right? Because 0 and b belongs to S, therefore is not an m-body. And another, so can we see, we can use these results for any x belongs to S, and we know the absolute of x is controlled by the absolute value of d, and I say by the results from 2. Does this make sense? Okay, and because d, the point d diverge, remember outside of d all diverges, right? So for the converge point, that should be inside of d. Therefore, is this true? Yes, right? Okay, so if we have this, means what? Means x is controlled by d, therefore d is a upper bound. Okay, so now we have these results. Therefore d, absolute value of d, is an upper bound. That does make sense? Upper bound of S, of course. If I draw a graph, now what do we have? We have this kind of results so far. And the x, okay, the middle center is 0, so I put 0. And then now we say the absolute value of d is upper bound. Absolute value of d is upper bound, so this is negative. Okay, therefore what? Therefore, because 0 belongs to the domain, therefore where is the domain? So our domain probably looks like this. Include the 0, right? Of course, if you look at the b, also b is in the domain S. That does make sense. So I put an S here. It's not exactly so far. We just have a basic idea. Just the S is inside of this negative d to d. Okay, inside. But now we do. Where is R? And we do have what is R. Okay, if we use these results by completeness. If someone remember this, completeness action, and we learned from section 11.1 at the beginning of sequence. This action give us, if we have an upper bound and then we have a least upper bound, right? Then it exists a least upper bound. Okay, we say is least upper bound, and if let me notate it as R. And now this R is what we need exactly. Okay, so let me highlight where is R. So you can see R is at here. Okay, and so this point we're going to say is negative R. R is a positive number. Okay, is a positive number. Okay, so that does make sense. Okay, so now all we need to do is just verify this R is what we need in case 3, which means all the x inside the R neighborhood converge, outside of R neighborhood diverge, right? So we're going to show these 2 steps now. And the first we say is this, is the outside of R, which means when x absolute value of x greater than R. The second case is absolute value of x less than R. which means the first case is outside, the second case is inside. And we look at the first. That's easy. Because what? Because this time we say X does not belong to S. Why? And because R is the least upper bound. Okay, upper bound, least upper bound, which means the minimum upper bound still upper bound, right? Still upper bound, and therefore X greater than the upper bound. Therefore X is not belongs to S, right? This makes sense. And in this case, which means what? Which means our series, okay, Xn is diverge because X is not belongs to the domain. Diverges. See, good. We proved the first, right? Now we look at the second. And inside, okay, so I have to show on this graph. If X is inside of R, which means if I pick if X is here, okay, so you will say X is belongs to S. No, we are not sure so far, but we can show. So how? We can do this. I will still use this color. Can you see? I will use this. Because what? Because R is a least upper bound. Do you remember what it does least upper bound mean? Which means between any number X less than R and inside we can find another number. Okay, if I say that the number is X prime, so X prime should be belongs to S. Do you remember this? That's the definition of a least upper bound. Therefore, now we can write it down. We can find X prime belongs to S, and X prime greater than the absolute value of X. Okay, good. So now we can find something. We can find what? Because this X prime belongs to S. Therefore, this is a convergent point, right? Therefore, our series here, X prime raised to the nth power, and our power series converges this time. Okay, and because this converges, so what? So we can get X is converge. Imagine why. So now we definitely can find this. C and X raised to the nth power converges to Y. Of course, we have a result is from the first step. Do you remember? Why? Because X prime, this is a big X. See, X prime converge. So inside of any number should be converged, right? X is inside of X prime, therefore is converged. See, that's the proof for this case. And then now we go to the last step. Here is the last step. Now we can prove the theorem for the power series not centered at 0. If it's centered at A, which is not 0, all we need to do is to substitution. Use the results from step 3. So let me see. Okay, so our series now is this. For this case, Cn X minus A raised to the nth power, right? See, and this time all we need to do, we just do this substitution. Okay, we just use this U equals X minus A, and if I put this, see, and we will change our power series to the one of centered at 0 for U. Is this centered at 0? Yeah, definitely. U minus 0, right? Okay, therefore we can use the results from step 3. See, now just by step 3, so we have this. We can find R, okay, radius of a convergence, right? And so we have these two results inside of R, and the power series converges. Okay, converges outside of U diverge. And this is the result from step 3, right? Now, how do you go to our series? And the back substitute, right? So now we do back substitute. See? And easily to find our results. Now it is for because U equals what? Because U equals x minus a. Therefore, x minus a, the absolute value less than R converge. And U greater than R, which means x minus a, absolute value greater than R. This is a divergent. Can you see? Is this the theorem? Yes, definitely. So that's all the proofs. That's all. Thank you. I hope you enjoy learning on this topic. If you have any question, please leave a comment. If you like this video, please give me a thumbs up. Thank you for your support. Please don't forget, you are very welcome to subscribe to my channel for more videos. In the next video, let's see. We are going to deal with the representation of a function as a power series by manipulating geometric series. Hope to see you there. Thank you. Have a nice day. Bye.